We are now going to draw the molecular orbital diagram for nitrogen monoxide, which is heteronuclear. So heteronuclear means two different nuclei, nitrogen and oxygen. So there's going to be some differences from when we draw with homonuclear. So first of all, this has 11 electrons. And so the question is, would we draw it this way or would we draw it this way? So if we use formal charges, we would see that on the left here, we would see that the formal charge on nitrogen is 0. That's 5 valence electrons minus 1, 2, 3, 4, 5. So that's 0. And on oxygen, it's 0. 6 valence electrons minus 6. 1, 2, 3, 4, 5, 6. On the right structure, on nitrogen, it would be minus 1. And on oxygen, the formal charge would be plus 1. So using formal charges, that would be our structure. We'll see in a minute if molecular orbital theory goes along with that. Now you'll notice something right away, that oxygen is lower than nitrogen. Now why is that? This is important, and it's very simple. Oxygen has greater effective nuclear charge. Okay? Has a greater effective nuclear charge, so that means that the electrons are going to be drawn closer. Notice I only drew the 2s and 2p. Also, oxygen is more electronegative. Okay, so that's why oxygen's orbitals are lower. All right, let's go ahead and populate those orbitals. Nitrogen has 5 valence. Again, we're only showing the valence, so nitrogen has 5 valence electrons. Oxygen has 6. Okay, and oxygen has 6 protons. Nitrogen has 5. Oxygen has greater effective nuclear charge, and as I said, greater electronegativity. Okay, so we're going to go ahead and draw our bonding and anti-bonding orbitals as we have in the past. Try to get that in the middle. So it's lower. So this is going to be sigma 1s, 2 electrons there. Sigma star 1s. I'm sorry, that should be 2, not 1, because we're on the second level. And there's 2 electrons there. So that's not really any different. But you'll notice that the bonding electrons are closer to the oxygen's 2s. Okay, now is when it gets a little bit complicated. So how are we going to populate the P? All right, so as you could see, there's 2 bonds. Well, experiments show that it's a little stronger than 2 bonds. So if you remember, oxygen O2 has 2 bonds, and nitrogen has 3 bonds. As it turns out, in terms of bond strength, nitrogen monoxide is in between those two if you just look at the bond strength experiments. So molecular orbital theory will help us with that as well. All right, so first comes pi 2p. Then comes sigma, and I need to raise the oxygen just a little bit here. It's still lower than nitrogen. Okay, so we're going to next have sigma 2p. So pi comes first. When there's a bond between nitrogen and oxygen, then sigma. Okay, up above our anti-bonding orbitals, we're going to have pi, and that's going to be pi star 2p. And then lastly, sigma star 2p. Okay, let's populate those orbitals and let's keep track of our electrons. So the pi 2p, those are degenerate. They're on the same level, so they're going to fill up like this. 1, 2, 3, 4. So we have 2 bonding orbitals, and then for the sigma 2 pi, we'll put both of those in there at the same time. And now we have 1, 2, 3, 4, 5, 6, 7, and we've used 6. So now we have 1 electron left, and it's going to go in the pi star 2p, antibonding. Okay, so if we want to find the bond order, that's going to equal 1/2 the bonding electrons minus the antibonding electrons. Okay, so how many bonding electrons do we have? Let's highlight those in blue. We have these. Those are all bonding electrons. So that's 2, 4, 6, 8. And we're going to subtract the non-bonding electrons. We'll highlight those in pink. We've got 1 there and 2 there. So that is minus 3. So 1/2 of 5 equals 2.5. So the bond order equals 2.5. And I told you earlier that it's in between oxygen and nitrogen, the bond strength as it's been measured. All 3 of them have been measured, and nitric oxide falls in between. Okay, so now which structure is it? Is it going to be the one with the lone pair on oxygen? I'm sorry, the lone electron on oxygen, or is it with the lone electron on nitrogen? Well, you should notice right here that this single electron is closer to the nitrogen than it is to the oxygen. So this orbital right here receives a greater contribution from the nitrogen 2p than it does from the oxygen 2p. That signifies that that is the lone electron. It's an antibonding electron on the nitrogen that occupies the antibonding orbital. So molecular orbital theory is consistent with our formal charge. One last thing I'd like to mention is, what if we did this? What if we did a plus charge on NO? So you might think, well, this doesn't look too stable. It's got that 1 electron, and that's not a very stable configuration. In fact, this is a very reactive gas. It's poisonous, it's very reactive, and it's, let's see what would happen if we gave away that electron to some other species that came along that oxidized it. So let's take a look. If we were to take this electron away, what would happen? Well, now our bond order would be 8 minus 2. That gives us a bond order of 3. And nitrogen, this oxygen-nitrogen ion, NO+, has a triple bond. That's been determined. And it is much more stable than that, the nitric oxide, but it has a plus charge on it. So we've used molecular orbital theory to observe a species in which the two atoms are from different elements.